Hi, I'm Lara. I'm a solutions architect at Databricks. In this series of videos, we're going to show you how our developers can leverage the Databricks Lakehouse. So we're going to show you how to connect to workspaces, how to create and manage clusters, and how to kick off jobs for your R workloads using Databricks workflows, and how to interact with things like MLflow models. And the key reason that you would want to do this as an R developer is that Databricks gives you access to elastic, reliable backend compute so that you can run HPC and distributed workloads on demand. And the great news is that you can also connect Databricks to your POSIT workbench, which provides you with a first class developer experience in R. How are we going to do this? We're going to split this in two parts. In the first part, Nikolai, my colleague, Senior Solutions Architect at Databricks, is going to show you how to use R in Databricks notebooks. And then in the second part, Trevor, Senior Solutions Engineer at POSIT, is going to show you how to use the POSIT workbench when connected to Databricks. So two different ways to use R in Databricks, very integrated together. And if you'd like to code along, feel free to check the GitHub link below.
I'd like to start by showing you how we can define clusters or backend compute in Databricks and how we can attach the compute to a notebook so we can execute our code. The process is very straightforward. I'll go to compute, and you see that I already have a number of clusters predefined, but to walk you through the setup, I'll just click Create Compute. And then you see I have a number of options. First of all, I can pick between a single node cluster, which means just one probably large VM with multiple cores, so I can parallelize my high computationally demanding workload, or I can go into a proper cluster with multiple worker nodes where I can distribute the computation in case I'm doing something like a heavy ETL type of workloads or data ingestion preprocessing type of work. You see that there is also access mode for the cluster, and in this case the cluster will be assigned to me only, but we can change this and go with shared clusters where multiple users, maybe my department, can share a larger cluster and work together. So the next thing I need to do is I need to select the type of the nodes that will be included in my cluster. And by default, I'm using something fairly small, 16 gigs of memory, 4 cores. But with a single click, I can go to something much larger, maybe 64 cores. And don't forget, that's just one of the worker nodes. So we can have multiple worker nodes, 64 cores or 96 cores or whatever we need with hundreds of gigabytes of memory available. The clusters can also auto-scale. So we can set up a minimum number of workers. That's how the cluster gets started with, let's say, in this case, only 2 workers. And then we can set like an upper bound, maybe 8 or 10 or whatever we think is appropriate. And then if the cluster experiences heavier workloads, it will automatically spin up additional nodes so the tasks can complete in time. We can also terminate the clusters automatically to save costs if we want to. And then also we can add some more advanced configuration to the cluster around running init scripts to prepare other aspects of the cluster. Or we can use Docker images for the nodes of the cluster if we want to customize the operating system with additional packages or some more specific configuration. That's also a possibility. Once we have the compute cluster defined, next thing I want to show you, I'll just use this one, is that we can also attach libraries to the cluster. And in this case, you see that I've attached a number of libraries. So when the cluster starts, the libraries get automatically provisioned and made available on the cluster so that everyone that's using the cluster has access to them and they don't need to install them on the fly. And we can always define additional libraries here. You see that you can install packages from the file system. This can be like custom R packages, or we can pull packages from PyPy if we want to use Python on the cluster as well. Or we can install R packages by default from the Crown repository, but you can provide a specific repo. It can be like an internal GSK repo, or we can point the cluster to the deposit package manager and install from there as well. Once we have the cluster up and running, we can go into one of our notebooks, and you see that the notebook has a default language here, which is R, but we can change individual cells to different languages. So in the same notebook, we can mix SQL, Python, R, as we see fit. And then here in the top right corner, we can see what backend compute is connected to this notebook. That's one of my clusters. And I can click on it, I can look at the configuration and restart the cluster, look at the logs, or I can, with a single click, change the compute resource behind the notebook, and now I'm attached to the other smaller cluster. Okay. Next thing I'd like to show you is how we can parallelize our code in Databricks using some default R packages. I have a notebook here. It is connected to a relatively small cluster, single node, 16 gigs of memory, 4 cores. I've already executed it because it takes some time. I will walk you through the notebook, but I just want to show you the results first so we can re-execute it with more powerful backend compute while we talk. So the first simulation takes about, as you can see here, 12 minutes. The second one, slightly over 3 minutes using the small cluster. So what we can do now is we can just switch the cluster with a single click. We can go to this one. Yep. And then we can run the entire notebook. Okay. And now you will see that the cluster I connected to has 128 gigabytes of memory and 32 cores. Now, you see here that we started executing the notebook already. It is currently running this piece of code you see here. And what happens is first we load the number of R packages that we need for the parallelization of the execution. They are already available on the cluster, but we just check, and we can also, the code installs them on the fly if they're not available, in case we attach the notebook to another cluster that doesn't have them. Then I have a piece of Python code because I wanted to show you how we can mix and match R and Python in the same notebook. So here you see I have this Python magic that tells Databricks that that's actually a Python cell. And what I do is I just look at the number of cores and threads per core. And when this thing got executed with the new cluster, it changed to 32 cores, 2 threads each. And we can, of course, get the same information through R, but I just wanted to show you that we can mix and match code. Now, the big piece of code that is currently executing is essentially, it generates some random data and then it fits a random forest model using Ranger, and it tries to do this in parallel using for each and do parallel. And you see here that while we were using the smaller cluster, the 4 cores, 2 threads each, it took about 12 minutes. We saw it before I reconnected to the new cluster and restarted the execution. And now, with the more powerful backend compute that provides 32 cores, the execution took less than 2 minutes, so 1.51. And the other piece of code uses a BRMS, and again, it analyzes like a sample data set, trying to run multiple chains in parallel. And we use RStan and compiles the code for the simulation using the GCC compiler, which is available on the worker nodes and the driver node, because it's a single node cluster. And we run 32 chains, and again, we try to parallelize them. So currently the program is compiling, and we can see how quickly it will execute as well. Okay, compilation has succeeded and we're now running the chains. Okay, so it took us slightly less than 2 minutes. Okay, that's what I wanted to show you. Next, I'd like to show you how we can use the STAN modeling language in a Databricks notebook. So here I have a notebook. The notebook is connected to a single node cluster with 16 gigs of memory, 4 cores, and it's fairly straightforward. So first we load the RStan package. We can install it on the fly if it's not available. Then we set some options for the package reflecting the number of cores available in the backend compute so it can parallelize the computation efficiently. And then we have a small hello world type of program written in STAN. It comes from the STAN documentation, deals with schools, effect sizes, and so on. So we have the program in DBFS in a file in the Databricks file system, but we can also have it as a simple R vector and pass it like this to the RStan package. And then we generate some artificial data. So we have 8 samples with the effect size and the standard error. And all we need to do is we need to call STAN, and then it will compile the code, run the simulation chains, and yep, we'll get the results and we can see them here. So it is again fairly straightforward. Next, I would like to show you how we can parallelize Python code in Databricks. Generally, in Databricks, we use Spark as the engine for large-scale distributed data processing, but sometimes you have workloads that are more computationally intensive and run on a single node, not necessarily distributed. Python, by nature, is single-threaded, so if we want to parallelize the execution, if we're running simulations or fitting multiple models in parallel, we can use Ray, which is another high-performance distributed computing framework for Python. Now, Ray can parallelize Python code within a single node, or it can also be run in a distributed fashion with multiple worker nodes, and then it will distribute the computation and also parallelize within the worker nodes. So in this notebook, I want to briefly show you how we can use Ray on Databricks. There is a helper function here, and you can look at the signature of the function that will set up your cluster on top of the Spark engine running in Databricks. So let me just run this because it will take maybe a minute to set up our cluster. And you see here that I'm connected to backend compute that has proper distributed Spark cluster. So we have a driver and we have, you see here, 4 workers, 64 gigs, 16 cores each. And what I'm doing here, I'm calling the setup Ray cluster function, and I'm saying, hey, I want you to set up a Ray cluster that has 4 worker nodes and 1 head node, which coordinates, but also acts as a worker as well. And in this case, we're not using any GPU accelerated backend compute, although Ray supports GPU acceleration as well. And you see here that the function is working. It is being executed as a Spark job. You can see here because it is setting up Ray workers on the Spark worker nodes as well. So it's like overlaying it on top. And any minute now we will have our, yep, here it is. Our Ray cluster is up and running. We can call ray.cluster resources to see the total amount of resources available. And we see here that we can use 16 CPUs, we see the IP addresses of the different array nodes, the total amount of memory available to the computation, and so on and so on. So to show you how our array parallelizes Python code, I have here a simple function that uses Monte Carlo simulation to try to approximate pi. So I will just run this cell. It's not executing anything, it's just defining the function. And what I will do here, I will run the function for 30 million samples, so 3 times 10 to the 7th. And in vanilla Python, the execution of the 3 batches, 10 million points each, is serialized. So this kind of takes a while, so it will take about 10-15 seconds. All right, here is our results. Yeah, close to 15 seconds, and the approximated value is 3.14. That's exactly what we expect. And now if we want to parallelize the computation using array, all we have to do is we need to create a wrapper function with the array.remote decorator. This tells array that this function can be executed in parallel. And then I have another function here that loops over the 3 batches, 10 million points each, and then just calls the wrapper function, which array can do in parallel, right? So we loop over the 3 batches, we calculate the approximated value of pi, and then we collect the results, again in another loop. So I will run this thing, and you will see now that unlike with standard Python, the computation is not serialized for the 3 batches. They're all submitted at the same time, and the results come almost at the same time as well, because the computation ran in parallel, and we have our value, which is 3.14, but it only took us 5 seconds or so. And the good thing is that we didn't have to touch the original Python function. So we just created a wrapper around this function. So it's very easy to migrate or port existing Python code to work with Ray. Also, Ray is more of the way I think about Ray is like a framework for building frameworks. There are multiple projects available on top of Ray which use Ray as a parallelization engine but provide higher level APIs. For example, RayTune is one of them, which is a framework for finding hyperparameters and hyperparameter optimization in general. And it's super easy to use it. Here you see another example. I define an objective function, just a quadratic that I want to minimize. And then I have some kind of a search space. And I can call RayTune and ask RayTune to do like a grid search over the search space and minimize the objective function. And this goes again through Ray. And you'll see that everything gets executed in parallel very quickly. So it just ran 4 tests in parallel and produced the best hyperparameters from the search space. There are also many frameworks that provide backend integration with Ray. For example, PyTorch, XGBoost, and so on. So here I have a snippet of code that uses XGBoost with Ray backend to train a number of XGBoost models. It is all done in parallel. You can see how the computation progresses, and very quickly you can fit a number of decision tree models and get the one that performs the best. You see here that the trainer recognizes the 4 available 5, including the driver array nodes, and parallelizes the execution. And we have here the hyperparameters of the model that performs the best on this specific dataset. Finally, as a best practice, it is always good to shut down your array cluster after you're done, so we'll do this. And that's all for this session. So another question that we received while we were discussing the use of R on Databricks was around the compatibility between packages that you currently use in Warp and if the same packages can work in Databricks as well. So we received a CSV file that contains all the packages that are currently available in Warp, and we wanted to test them on Databricks. So I put together this very simple notebook that reads the packages.csv file from the file system, and then it collects the packages that are currently installed in our default R distribution. And then what I saw was that the number of packages in the CSV file that we were provided was 602. Out of these 602 packages, 228 were already part of the R base that we run in Databricks. So we had to test something like 478 packages, which was the difference between the two. And you see that this matches not just the package, but also the version, right? So I wrote this simple snippet of code that goes over the CSV packages, and if they're not installed, if they're in the diff, it tries to install them on the fly just to test if they work. So out of the 400 and what did we say, 78 packages, pretty much all of them were installed except 22 packages or so. And these 22 packages, they were either GSK proprietary packages that were not available in CRAN, or there were packages that had like custom installer that were again not, we were not able to install by just saying packages.install. So what I did is like I picked one of these packages here that wouldn't install, which was the which required its own installer through BIOP Manager, and yeah, it installs fine. So it is a question of going through which packages were not available in CRAN or weren't available for direct installation, and just like manually install them. But yeah, I'm fairly certain that all the packages we can get across and make them available in Databricks as well. And of course, you don't need to install them like one by one. You can add them as libraries to the cluster, or you can customize a Docker container and so on, and provide a pleasant experience so people don't need to install them on the fly every time. Okay, that's all I had for this one. What I would like to show you now is how we can use Sparkly R in Databricks. Sparkly R is a package that is essentially an interface to Databricks Spark from the R language. And what I'm currently doing here is I am running a SQL query against a sample of the TPCH benchmark. So, and you can see it is still running currently. I am connected to a standalone single node cluster, so just one VM, 16 gig of memory, 4 cores. And I'm running one of the relatively difficult queries from the TPCH benchmark. I think that's query 9, that joins multiple tables and groups by various columns and like aggregates data. So the point is that this table is actually in Unity catalog. So if I go into catalog, there is a samples catalog and there is TPCH in my workspace, and I'm running a query against these tables here. And to be able to do this using Sparkly R, I just need to load Sparkly R. Then I need to connect to Databricks, and you see that it's fully integrated. So I don't need to pass manually credentials and authenticate. There is like an automatic pass-through. I can set the schema that I'm interested in for running queries, or I can just distribute our data frames directly to Spark from R. I don't need to run SQL queries. But here, because I'm using TPCH, I'm just running a SQL query, and here is my query, and yeah, I'm just running it, and it's still ongoing. And when this thing completes, then I also wanted to show you that Sparkly R is compatible with dplyr as well. So we can just grab like a sample dataset like iris. We can say copy to and provide the Spark context, which is like the connection to Spark. And then this dataset gets distributed on the Spark worker nodes if we have multiple worker nodes, and then it's available as a Spark table and a Spark object that we can interact with. And we can run operations like, for example, count. And if we have multiple worker nodes, this operation gets parallelized and execute it in parallel. And then I also have a bit of code that uses ggplot2 to like plot a table, and again uses kind of a dplyr syntax to group different things. So let's see how long this takes to execute, and what I'm planning on doing is then after this thing is finished, we'll just switch the backend to something more performant, and then we'll see what happens. Okay, so we can observe the various Spark jobs currently being run. Okay, so it took about 6.4 minutes to complete, and then the others, they're very quick, so they're already completed. So what I will do now is I will just go here and change to a cluster that has 2 worker nodes, 32 gigs, 8 cores each, and the driver is 16 gigs, 4 core. And I will rerun this query. Let's see what happens. You see that I'm not changing any of the code, any of the SQL. Spark handles the distribution of the tasks automatically. So let's see how long this one takes. Oh, it took us about 12 seconds. Right, and the others also run almost instantaneously. Okay, so that's how we can connect to Databricks Spark from R. What I would like to show you now is the R integration with MLflow. So MLflow is an open source platform for experiment tracking and generally end-to-end lifecycle management of machine learning models. It was created by Databricks and it's open source, but it's available as part of the Databricks platform out of the box. So I want to show you how we can use R with MLflow. And what I'm doing in this notebook is first I'm getting some freely available data from the UCI machine learning repository. So I'm pulling this data on the fly. And then what I've done here is I have created like a training function that splits the data into a training and test sets, and then it fits a predictive model using a number of hyperparameters like a learning rate and regularization that are passed to the function, and it also computes a number of model performance metrics like RMSE, R-squared, and so on. And when you look at the code, you will see that it also uses the MLflow API through the MLflow R package to talk to MLflow, and every time it trains a model, it not only tracks the hyperparameters that were used with the model and the model performance metrics, but also stores some artifacts with the model like a cross-validation plot, and also logs the entire model as a serialized object in MLflow so we can later use it for inference. So I will run this cell to define the function, and now I will call the function 3 times with different hyperparameters. And when we run this cell, you will see that we'll start fitting the model, and then every time we fit a new model and we train a new model and evaluate it, the results get stored in MLflow. We can actually see this in the UI. So if we go to experiments, let's open this in a new tab, and we go here, we will see that the 3 models are already here. So they train really quickly. So if I open any of these, I will see the hyperparameters that were used for training the model, the resulting performance metrics. I can also look at the artifacts, which is the serialized model and also the cross-validation plot. So if I want to then look at these different models to determine which one performs the best, I can simply interrogate MLflow, so I can connect, I can pull the results for, let's say, in this case, R² metric, and I can pick the model that has the lowest R². And this is the unique URI for the model, which I can then use for inference in another notebook or a script using R again. And yeah, this is very straightforward. So what we need to do is we need to just call MLflow, pull the model that was stored there based on the URI, and then we can just feed some new data and the model will generate predictions, right?
Posit Workbench is a centralized platform for doing data science development. Here I'm going to show how to launch an RStudio Pro session to use the IDE that you know and love together with Databricks. So from the Posit Workbench homepage, we can launch a new session. And if we know we're going to be working with a Databricks environment, our admins can set up credentials so that as a user, I click this box, I OAuth into Databricks, and now you'll see this check mark here indicating that this session will have credentials automatically set up so that connections to Databricks will just work. I can also select different resource profiles down here. And so in this case, in the demo, I could use a really small one, or I can customize and I can request more CPU, more memory, and I can also customize the image I want to use as a basis for this session. This is powerful because it allows the researcher or data scientist to go in and select the compute required for their session, select from an image that may have specialized software pre-installed, and also if you need further resources, you'll be able to then connect into Databricks. So here I'm going to start the session, and it will start up. And now that it's active, I can click in, and here I am inside Posit Workbench, inside an RStudio Pro session, able to start interacting with my Databricks cluster and do my normal R work without any further authentication here or any further setup on my desktop. I'm now going to launch an RStudio Pro session in Posit Workbench to explore the functionality around using multiple R versions and some of the benefits that brings. So here I'm going to start a new session. I'm going to make sure I have my credentials with Databricks enabled, and I'm going to select the resources that I need for this session. So I'll kick this session off, and as this is ready, I can join it. And by default, a certain R version will be launched, and this is configurable by your admin. So here you can see in the upper right corner, it's R 4.4.0. Let's say I had code that I needed to run on a previous version of R. Workbench makes this really easy. As a user, I can come up and I can flip to a previous version. And what this will do is it will launch the IDE ready to use a new version of R to do your work. Now, this is really powerful because we hear from a lot of our customers the need to test code on newer versions of R before committing that code to more production work. And also, sometimes we know it takes a while to update code to run on new versions of R. And so being able to run on historical versions and not need to commit to a new version is a very useful feature. So here you can see in this session, I'm now using R413, and this gives you the choice of what version of R you want to use, and administrators can keep adding newer versions and decide when they're going to take out support for older versions. A great benefit to doing your work in an RStudio Pro session running in Posit Workbench is the ability to do your work in RStudio and then seamlessly connect to Databricks to take advantage of all-purpose compute to run Spark workloads. And in this example, I have launched an RStudio Pro session with Databricks OAuth credentials already enabled. I showed this in a previous video, but we can see in this upper right corner that they're active here. And as long as this is established, as a user, I get rich information about my clusters in this Databricks pane. So here we can see the clusters that I have access to. I can see their state. These two are running, for example. I can also start and stop the clusters from this pane. And I can come and see configuration information and what some of the underlying compute is. So in this case, I can grab the configuration and I can start making Spark connections through sparklyr against this cluster. We'll cover some of the Spark workloads and connecting to Spark clusters in a different video. For now, I want to turn our attention to the connections pane, which allows you to explore from inside the RStudio IDE the Databricks catalog. So here I have a table, Winding Club, that I can see in my Databricks catalog. And I can also preview by clicking this button, and it'll open the first 1,000 rows in the RStudio IDE for me to look through the columns and do certain filtering operations. So this is really helpful because I am still within my RStudio IDE. I haven't had to go to the Databricks UI. I can figure out what columns I may want to work on, and then I can switch back to my code and I can make those adjustments and execute my code against Databricks without needing to go anywhere else or use other systems. The other thing to point out is, as I'm exploring this table, when I make connections and start pushing Spark workloads to the cluster, all of the Unity catalog permissions that apply will still apply here because I'm connecting to Databricks as my username, not as a service account or anything like that. And so if I have certain rows that I'm restricted from accessing, if there's masks applied or anything like that, that'll all be preserved. And when I make a Spark connection or even an ODBC connection to SQL warehouses, those connections will only retrieve data and only information that I have access to in Unity Catalog. One great benefit to using an RStudio Pro session within Posit Workbench is the ability to push compute to Databricks SQL warehouses. And you can do that seamlessly without managing your own authentication. So as mentioned in a previous video, when you start an RStudio Pro session, you get the option of establishing an OAuth connection to Databricks. So you can see that in this upper right corner. It shows that I am currently authenticated to Databricks as my username. This allows me, when I want to establish a connection to an SQL warehouse, to use the ODBC package and specify an HTTP path, which can be found in the Databricks UI. And all I need to do is run this command. And what this will do is this will start up my serverless SQL warehouse. It will show me catalogs I can explore here, which we'll dive into in a future video. And now I have a connection object that I can start making database calls against. Now in this example, I'm going to be using dbplyr, which is a way to take dplyr functions that you may already know and love, but have these convert behind the scenes to SQL. This is great because I can write the same code here and have this execute against an in-memory data frame that you're used to using, or I can establish a table like this, a virtual table. And this is pointing to a table in my Databricks catalog so that I can execute against large amounts of data and still keep this session manageable and using minimal compute. So once I have my connection here, I can see a preview of the query that will be executed. And so because I haven't actually pulled any data back in memory, when I execute this, I'll just see the first 1,000 rows. This allows me to build up my query and see how it's panning out without having to actually commit to bringing data back in memory, which is really handy if this table is quite large. I can also ask dbplyr to show me the query. And so you can see behind the scenes, you don't have to write any SQL, but dbplyr will write it for you. So here I can see the query that's been generated. And then when I actually want to pull data back into this session in memory, I can use the collect function. And so what this has done is, this is connected up here to a table in Databricks using SQL warehouses. I've used dplyr verbs that I'm familiar with. And when I call collect, only then is it taking this query, sending it to Databricks, executing on the data, and only pulling back the summary statistics that I require in my session. This is handy because the compute's done on the Databricks side, and then I can do something that I love R for, graphing, without having to have a lot of compute behind this session running in Workbench. One great benefit to using the RStudio Pro IDE within Posit Workbench for your workloads is the ability to reach out to all-purpose compute Spark clusters in Databricks and execute workloads there from the comfort of your RStudio IDE. I showed in a prior video how to start an RStudio Pro session with Databricks credentials enabled. Here we can see in this session in the upper right corner that I have a connection. And so once this shows, I'm now able to see what clusters I have access to in this Databricks pane. There is another video going over these panes in detail, but for now, I want to focus on a cluster that I have running that I want to use to execute Spark commands against. So here, I can grab my cluster ID. I can use the Spark Connect function from the SparkLR package, and I can make my connection. And notice there's no authentication needed here because Spark Connect knows where to look in Workbench for my user's OAuth token. So in the background, because this is enabled, I have short-lived tokens that Workbench refreshes automatically. And for you, the user, you just get to use Spark Connect without needing to think about how the authentication is being done, and it's being done in a secure manner. And so this allows me to jump into a session, establish a connection, and once this connection is made, I can then perform different workloads. And so one would be using dbplyr to take dplyr commands that I already know how to use, pipe them into a virtual table, and this behind the scenes will actually create SQL, which it'll push through SparkLR to Databricks and push this compute to the Databricks side where the data is, rather than needing to bring all the data in memory and then execute dplyr against it. So that's one option. You can do these SQL style commands, but there's also more to the Spark ecosystem that can be taken advantage of. So the SparkLR package has lots of great documentation on what's supported. You can use Spark machine learning functions. You can apply R code as user-defined functions. So you can actually push our code to run on the Spark cluster itself. And this allows you to take advantage of some of the distributed computing and additional computing resources available within Databricks for large jobs. And so one workflow we see is users coming in, using RStudio to get started, explore the data, maybe pull smaller subsets to do some training in this session. And then once they want to execute against a large amount of data where you need much more computing and it's more efficient to execute close to the data, then you reach for Spark and maybe use a user-defined function to take advantage of all that Spark has to offer. Shiny apps are important to many R users that want to create an interactive app that others can access without having to know how to code in order to do self-service analytics and other dashboarding type features. So here in RStudio Pro running in Posit Workbench, I have a Shiny app open, and I wanted to show how you're able to run, preview the app, do your typical development workflow, and then also how to deploy it so you can share with others. So in this session, I already have a Databricks connection here. I can see that in the upper right corner. I have a previous video showing how to start sessions with Databricks OAuth connections established. Once this is here, I'm able to work on an app that's connecting to an SQL warehouse in Databricks through ODBC. I can do that without any authentication because, again, it's already activated here, and the ODBC package knows how to read these credentials automatically. So all I need to do is run this app. I can see it in this viewer pane here. And you can see it will spin up an SQL warehouse, make that SQL connection, and then bring that data back into the app to be displayed. So here you can see is a dashboard that you would give to a user. You can make changes to the code. You can rerun it. You can see it in the viewer pane here, or you can have an additional window opened up for viewing that way. The choice is yours. Once you're happy with a Shiny app and you want to get it into the hands of users, that's where Posit Connect comes in. So far, we've been in Posit Workbench in an RStudio Pro session. But when we want to share this application to others in the company, that's when we turn to Posit Connect. And we use this Publish button up here, which is built into the RStudio IDE, to click. Select the files that we want to send to our Connect server, listed here. And when we publish, it's going to take all of these files that are needed. It's going to figure out what packages I use to author this app, what R version, and it's going to send all of this to the Connect server so that when the app needs to be shared with others, it will have the necessary components. So we'll wait for a minute here, and when this is done deploying to Connect, I'll get a link that I can start determining who can see the application. So here it opens up a window, and now we're in Posit Connect. And so we see the same app on the left that we authored, connecting to Databricks in order to pull data down from SQL warehouses. But on the right, now we have controls around who should see the app and how should it be running. And so I can select specific users to share. I can determine authorization settings around that. I can create a custom vanity URL that I can share with users so it's nice and readable. And I can tell it that Databricks should be used for OAuth. And this is important because when I share this link with the viewer, I'll show what this looks like here. It's going to pull up the app, and it's going to use my personal OAuth credentials to connect to Databricks to pull the data. This is great because if I share this with a colleague and they have different row level permissions, they're only going to see the data that they have access to. And so this allows you to develop a Shiny app based on data in Databricks without having to police the permissions, because all of the Unity catalog permissions that are set up will automatically be inherited from when the data gets pulled into the app. And so to review, I've started in an RStudio Pro session. I've authored my Shiny app connecting to Databricks. I've pushed it through this button to connect. And then from Posit Connect, I can decide who can view the app, what should it be named, what Databricks integrations are needed for the data to get pulled into this app, and so much more I can customize above.